Hello, Nee. You were asking why is N2F4 considered to be polar? Now, N2F4 is a little complicated because of its shape. So if you were to draw the Lewis structure, you would get the Vesper number to be 431. So it would end up being 431. So one of the central atoms, remember in this case, the thing about N2F4 is you have two central atoms. This is what it would look like. So the blue is the nitrogen. Okay, you have two nitrogens, and each nitrogen has two fluorines on it. Okay, the black thing, the ball, that's the lone pair. So that's the lone pair that's on it. It would be trigonal pyramidal, and this is the lone pair that's on it. So looking at this is what you would have. Okay, you would have the nitrogen in the middle. You have the fluorines just like this. And you have connected to it is the other nitrogen with the other fluorines on it. That's what we have right now. Okay, this is what you have. Now, the green is the fluorine, and the green is the more electronegative part. So everything is being pulled in the direction of the green balls. Now, what makes this difficult to explain is that the bond in the middle, the nitrogen can actually rotate around. Okay. So if you remember, the electrons want to be as far away from each other as possible. So when it's like this, remember the black things are the lone pairs. When it's like this, the electrons are close to each other. They don't want to be close to each other. Remember, they want to be as far away from each other as possible. So actually, this would rather be like this. It is free to rotate, but when it's like this is when it's the happiest because the electrons are as far away from each other as possible. Now, when it's in this position, these fluorines are up and these fluorines are down. So this is going to be pulling up towards it, but these are going to be pulling down. And so they would cancel in this position and in this position only. But because this is free to rotate, even though it's happiest when it's like this, sometimes it isn't always like that. It can move around and change locations. And when that happens, the pulls no longer cancel. When it's like this, all of them are facing down. And if they're all pulling down, then you're going to have a polar direction going downward. So it depends on the bond rotation and where it is. When it's in this position, it cancels. They do cancel and it becomes nonpolar. But when it's like this, they don't cancel and they actually add up. So the only time it cancels is when it's like this. But it can be in any position at any point in time. So there's only one spot where it cancels, and it's this. And this is actually its favorite spot because, again, the electrons are as far away from each other as possible. But it does move. Things do move. It isn't always going to be in one position the entire time. So to say that N2F4 is polar or nonpolar, the answer is it depends on the position it's in. Most of the time, it is going to be polar because in any other position, it doesn't cancel. The only time it's nonpolar is when it's like this, and that's when the poles cancel out. Okay, but this. I hope this answers your question. If it doesn't, I can try to explain it a different way if you need me to. But this is what N2F4 would look like. Okay. These are, again, the lone pairs. This is the lone pair here, the two dots. They both have a lone pair on it. And the green ones are the fluorine. Okay, when they're like this, they're all going down until they add up. When it's like this, two up, two down, this is when they cancel. Okay, these are pulling up and these are pulling down and they cancel each other out. But this is the only position where it does that. Any other position, the pulls don't cancel and you do get something that makes it polar. Okay, so the answer is it depends. But most of the time it's polar, and sometimes it's non-polar when you get into this position. Okay, hope that makes sense.